So about the IPCC AR6 Working Group 1 report published last summer, you may recall media coverage on the first statement of the summary of the policymakers, SPM, written here as, "It is unequivocal that human influence has warmed the atmosphere, ocean, and land." Now the report declares that the link is 100% sure. Since the pre-industrial times, the global surface temperature has already warmed by about 1.1 degrees Celsius. And the trend is well simulated in the climate model simulations, taking both of human and natural influences into account, while it is not in the simulation of natural influence only. And here we can see that we are approaching 1.5 or 2.0 degrees limit that Paris Agreement aims. The Working Group 1 assessment report consists of these 12 chapters, and the chapters after the framing section are subdivided into 3 parts: large-scale climate change, processes, and regional climate change. So from the processes section, the chapter 5 and 6 are the 2 major chapters where the atmospheric composition and their sources sinks are discussed. Greenhouse gases are for chapter 5 and the SLCFs are for chapter 6. The chapter 7 is also related, where the radiative effect is altogether assessed. So I will talk the main storyline from these chapters related to the chemical substances, including aerosols. For chapter 6, I served as a review editor. The lead authors from Asia for this chapter were Bhupesh Adhikari from Nepal and Hong Liao from China. And with the Working Group 2 and 3 reports for impact, adaptation, and vulnerability, and for mitigation, and upcoming synthesis report, the overall AR6 report will be completed. So first, the drivers of the past global warming from 1750 to 2090 are depicted here as a bar chart. Red bars indicate warming and the blue bars indicate cooling. So one big note might be that the x-axis here can be the temperature scale in AR6, while they were used to be the radiative forcing for the easier understanding for the public. But the overall features are almost unchanged from AR5. CO2 is most dominant, and methane and ozone follow, and the aerosols partly mask the warming. The atmospheric concentrations of all species increased from the pre-industry times to the present. And that drives the climate change, depending on their optical properties. And both positive and the negative effects appeared. But the one thing to note is that the aerosols has increased, but they're overturned already, and that will affect the future climate. The warming or cooling contributions per chemical species can be shown as their time evolution to provide more information. For example, occasional volcano eruptions shown in green cool the temperature and were the dominant features in the 19th century. However, these individual events lasted only for less than 10 years. After 1950, the dominant feature became continued rise due to CO2, methane, and ozone increases, which were partly compensated by the increases in the tropospheric aerosols, as seen in the last slide. Here, by identifying the large contributions of CO2, the D.1 statement of the summary for policymakers occurred as limiting CO2 emissions or reaching net zero CO2 emissions are required to limit the global warming. But here, another important point is that the cooling due to the tropospheric aerosol has peaked out, and now it changes to upward shift, namely the relative warming from now. This is due to declining aerosol pollution, as seen before. The scenarios intentionally maintaining the current level of tropospheric aerosols may continue to cool the Earth system, but are not recommended in terms of health and air quality. This is not my personal interpretation, but what IPCC report really said. So we have double pain from aerosol warming and CO2 warming. A possible remedy to this inevitable warming would be from rapid reduction of methane emissions. Thus, the second part of the statement says, strong, rapid, and sustained reductions in methane emissions would also limit the warming effect resulting from declining aerosol pollution. So this is the main storyline that I will highlight in the following slides. Here, the bars show warming and cooling contributions from species after 10 and 100 years of a hypothetical single year of emissions. For the 100 years case in the bottom, the CO2 in yellow is dominant, and this sure is the most important target of mitigation. But the methane contribution becomes relatively larger for the time scale of 10 years near its atmospheric residence time. And the breakdown of the contribution to emission sectors and to the emission regions suggests that CO2 from energy production and industry from East Asia, North America, and Europe, or methane from fossil fuel production, agriculture, and waste management from East Asia and South Asia as well, sometimes from Latin America, are dominant. Future temperature projections are the major output of the IPCC report and are often displayed with 5 core SSB scenarios, emission scenarios for CO2. The scenarios have their names such as SSB 1-1.9, but here we call them simply very low, low, intermediate, high, and very high scenarios, similar to the text in SPM. For example, in all scenarios, the temperature rise reaches 1.5 degrees Celsius within 20 years, but the differences become larger later. The Paris Agreement aims 1.5 or 2.06 degrees Celsius, and they correspond to very low and low scenarios where net CO2 emissions become zero or negative around 2055 or 2075. The intermediate scenario is set at the path we are now on. And the high and very high scenarios are based on more emissions in the regional rivalry or the fossil fuel intensive world. But the scenarios support not only CO2 emissions, but also all relevant SLCF species, including methane, black carbon, OC, SO2, NOx, CO, NMVOC, and ammonia, and HFCs. And they were used for the future projection and concentrations and impact. The basic feature might be similar to CO2, namely the low emissions in low emission scenarios, as generally controls pretty much similarly affect both CO2 and SLCFs. Area peaks for SLCFs, particularly for SO2 and NOx, than that for CO2 are to be highlighted. SO2 and NOx already peaked out, as removal technology application is easier than CO2. As they are major aerosol precursors, the aerosol pollution reduction has already started. From now, such trend will continue and the temperature rise is inevitable. In reference to 2019, the temperature rise due only to aerosol change will be at maximum 0.4 degrees Celsius in the case of very clean, very low emission scenario. And this warming effect could be limited by methane and ozone when methane emission reduction becomes successful, though not very easy now. As a lifetime of methane is about 10 years, its concentration will decrease pretty fast as the emission decreases in the low scenarios. And the cooling from 2019 is expected in the range of 0.1 or 0.2 degrees Celsius. When NOx is reduced, the tropospheric ozone formed by photochemistry of NOx and methane will also be reduced. and therefore the additional cooling is expected due to the ozone decrease. So together, that cooling will be in the range of 0.3 or 0.4 degrees Celsius by 2100, compensating the warming due to the declining aerosols. But this is only when the successful emission reduction for methane is achieved. So here's a net total effect from SLCFs, including aerosols, methane, ozone, and HFCs is depicted. All scenarios led to warming toward the 2100, but the range is wide, ranging from 0.1 to 0.6 degrees Celsius. As we saw at the beginning, when we aim limiting to within 1.5 degrees from the pre-industrial times, the allowed temperature rise from now on is only 0.4 degrees. Depending on scenarios, that allowance is easily filled by the change in SLCFs only, not by CO2. Therefore, controls of SLCFs are also important as well as that for CO2. This situation is demonstrated in another way. The global surface temperature increase since pre-industrial times is said proportional to the cumulative CO2 emissions since 1850. This is a concept of the carbon budget. The temperature rise in the past by 1.1 degrees corresponds to the equivalent total CO2 emissions so far. To the target of 1.5 degrees Celsius, the margin of 0.4 degrees might correspond to the remaining carbon budget of this width of about 800 gigatons CO2, but it is not in reality due to the presence of non-CO2 or SLCFs. So we need to allocate a part of the temperature margin to SLCFs to by about 0.2 degrees, as we saw in the last slide, even in the smallest case. In the remaining carbon budget, the allowed CO2 emission from now must be diminished to 500 gigaton CO2. Considering the recent annual emission of CO2 of 43 gigaton CO2, this corresponds to only 12 years of emission. This is why urgent emission reductions are seriously discussed. The partitioning is also affected by the process representation uncertainties in the model, such as the potential feedback from more frequent forest fire occurrence. Therefore, the behavior of SLCF species determines the maximum CO2 amount allowed to emit, and thus they are important to study. The warming from reduced aerosol pollution mentioned so far was already demonstrated during the COVID-19 lockdown period. Limited human activity in 2020 resulted in about 5.4% reduction in the CO2 emissions and must have resulted in some cooling in comparison to the case without the reduction. However, the aerosols were similarly reduced by the reduced human activities, as depicted by the green color here, showing the AOD reduction over Asia particularly. The media also showed blue sky is returned over in India, where otherwise the hazy condition was typical. Such reduced aerosols increased insolation to the ground and must have induced warming. The two counteracting effects, heating by reduced aerosols and cooling by reduced CO2, must have compensated each other, and temperature change from simulation models remained almost unchanged.